Hello everyone, today we're going to start section 6.1 on exponential growth and decay functions. As a quick review, go ahead and pause the video and try condensing the log function shown below. The first thing we need to do when condensing log functions is to make sure to put coefficients back into our log functions as exponents. So this would be ln 3 plus ln of x to the fourth minus ln of y. From there, we work left to right with our addition and subtraction. So here I see addition. That will translate to multiplication inside the log. So 3 times x to the power of 4 minus ln of y. We continue working left to right. The subtraction implies division inside the log. So 3x to the fourth over y, and this would be our condensed form. Today we're going to move forward into exponential growth and decay functions. Exponential growth and decay have the form y equals a times b, where b is raised to the power of x. The growth factor is the base of your exponent. So for example, in number 4, I have y equals essentially 1 multiplied by 8 to the power of x. So that growth factor is going to be 8. We're multiplying by 8 over and over and over depending on what our x value is. If x was 3, this would be 8 times 8 times 8. If x was 2, it would just be 8 times 8. So the growth factor is the number that we're multiplying repeatedly. Our initial value is the number in front, or the coefficient on that 8. This is the value that you're starting with in your growth or decay function. Here in number 5, our growth factor is going to be 5 over 3. Here our growth factor is 2/3. Here our growth factor is 2.5. Here our growth factor is 0.4. And here our growth factor is 0.1. Now what determines whether this is a growth or decay function is whether the growth factor is greater than 1 or less than 1. So for example, in number 4, our growth factor is 8. Since we're multiplying by 8, our values will get bigger, and this will be a growth function. 5 divided by 3, 5 over 3 is a number that's greater than 1. So when we multiply by that value of 5 over 3, we will increasingly get larger, so this would be a growth function. But when we multiply by 2/3, 2/3 is a number that's less than 1. So when we multiply by 2/3, our values will get smaller and smaller, making this a decay function. Here I have 2.5, which is greater than 1, so this would be growth. 0.4 is less than 1, which would be decay. 0.1 is less than 1, so this would also be decay. Down below, take a moment to pause the video and try these couple on your own. Our growth functions are y equals 3 to the x and y equals 5 to the power of x. The one that's going to grow the fastest is the one with the largest base, which would be y equals 5 to the power of x. The slowest decay, my decay functions are 1/5, 1/3, and 1/7. Now since this does say slowest decay, we want the one that's going to stay large as long as possible. So essentially we want the largest value that is still decaying, and that would be our 1/3. So even though this one is decaying, it's decaying at the slowest amount. Multiplying by 1/7, our numbers get a lot smaller much more quickly because that number 1/7 is significantly smaller than 1/3. To graph, we're going to go ahead and create a chart and sketch a graph of our functions. So I have my x values and my y values. The x values I'll plug in would be -2, -1, 0, 1, and 2. My y values then would be 3 to the -2nd, which would be 1/9. 3 to the -1st would be 1/3. 3 to the power of 0 would be 1. 3 to the 1st would be 3. And 3 squared would be 9. I'll graph this first function in red. -2 and 1/9 is going to be a very small number. Negative 1 and 1/3 is still fairly small. 0, 1, 1, 3, and 2, 9. Now when I think about connecting these dots, I need to be careful because no matter what value I put in for x, my y value will never drop to a negative number. If I think of putting in any number for x, maybe negative 5, that is never going to make the answer negative. What it's going to do is turn my 3 into its reciprocal. It'll drop it down to the denominator. It will never, no matter what this value is, change the sign of 3 to negative. Neither will we ever be able to get a 0. So if I put a 0 in, we know that's going to give us 1. If I put a positive number in, this just gets increasingly larger. There's no number we can put in to get 0 or negative. So we have an asymptote here at 0 that we're never going to touch and we're never going to cross. So when I sketch my graph, it's going to hover right along that line and then increase to the right. Looking at my 1/3 when I create my chart, I'll use the same values, negative 2, negative 1, 0, 1, 2. 1/3 to the negative second. I take the reciprocal and square it and I get 9. 1/3 to the negative first, I take the reciprocal, which is 3. 1/3 to the power of 0 is 1. 1/3 to the first is 1/3, and 1/3 squared is 1/9. Connecting these dots, negative 2 and 9, negative 1 and 3, 0, 1, 1, 1/3, 2, 1/9, and again we're never going to touch or cross that x-axis. So these end up being reflections of one another. On the right, I have this graph that goes up in red. This is our growth function. As we move to the right, my function is increasing, meaning we are growing. As we move to the right on the blue, however, we are getting smaller, meaning we are decaying. We can also go back to looking at our bases. I have a 1/3 and a 3. We can see based on the equation that these would be growth and decay functions. Go ahead and take a minute, pause the video, and try sketching these couple on your own. My first equation we know is going to represent a growth function because that base is larger than 1. When I go to create my table, I plug in the values negative 2, negative 1, 0, 1, 2. We should have 1/4, or if you're using a calculator, maybe you use 0.25. Here I'd have 1/2 or 0.5, 1, 2, and 4. So my graph is going to look something like this. And again, never touching or crossing that x-axis. It is a growth function, so we should expect it to start low on the left and go up to the right. A couple key points here is that it will always cross through that point 0, 1. And 1, comma, your base. 1, comma, b, which in this case is 1, comma, 2. Those are a couple of key points that we are always going to have on our standard graph. 1/2 to the power of x, I've got negative 2, negative 1, 0, 1, 2. This will become 4, 2, 1, 1/2, and 1/4. Negative 2, 4. Negative 1, 2, 0, 1, 1, 1/2, 2, 1/4, and never touching or crossing that x-axis. If we see on this, there is still that point of 0, 1, which is going to be on all of our parent function graphs. And then I should expect the point 1, b. My b is 1/2, so here is 1 and 1/2. That point, sure enough, is on my graph. All right, go ahead and take a moment, pause the video, and try these two more on your own. I do know that this will be a growth function. I know that I'm going to pass through the point 0, 1, as well as the point 1, 4. So I can put those on my graph, 0, 1, and 1, 1, 2, 3, 4. From there, if I wanted to just sketch a general picture of my graph, I could connect the dots, and it would look something like this. Number 2 would be a decay function because my base is less than 1. And I know that I'm going to pass through 0, 1, so I can put that point on my graph, as well as the point 1, 2/3. So 1, 2/3 would be right about here, and a general picture of my graph would look more or less something like that. Our last page, we are going to use the graphs to identify the base b. We know that all graphs, as long as the coefficient is going to be a 1, we're going to talk about those vertical stretches in a future lesson. But here, my graphs are going to pass through the point 0, 1, as well as the point 1, b. So all we're going to look for in order to determine the value of b is we are going to look for this point on our graphs. So in our first number 10, I see that point here, 1, 2. So that means that my b value has to be 2. In the second graph on the right, I see the point 1, b, which means my b value is going to have to be 8. Go ahead and try the next couple. In number 10, I see 1, 10, which means my b value is going to be 10. And here I see 1, 1/3, which means my b value is 1/3. We could go ahead and write the equation all the way out. F of x is equal to 10 to the power of x, and f of x equals 1/3 to the power of x. That brings us to the end of our first part of this section. Thanks so much for watching, and have a great rest of your day.